Hello everyone, it's Mr. Wolf here, and in this video I'm going to be going over the concept of work in our energy unit. So in class, we showed two demos, and I'm going to kind of just draw them up here. And the first one was a car going down one of the ramps, and then it was on the table, and the car started on the top of the table, and when it went to the bottom of the ramp, went across the table, it eventually stopped. Right, so that was our scenario. So if we were to draw an LOL for this, by the way, where this is KU, O, L over here, KU, right? What ended up happening, or what we would end up drawing, is at the beginning, it's at rest, so no kinetic, has a height, so it has potential energy. And then at the bottom, we could say that's 0 meters, so no potential energy, and no kinetic energy, because like I said, it stopped right here. Right, so if we look at our LOL, it looks like we broke physics, because we know that we can't create or destroy energy, and that's exactly what happened, right? There were 4 blocks and then there were none. Right? So we didn't really break physics, but we have to introduce this concept of work now. So what ended up happening is this system that we're drawing is the energy of the car. Right? And even though energy can't be created or destroyed, it can transfer in and out of systems. So what ended up happening is when it was going against the ground right here, there was friction. Right? And that friction caused energy to leave our system. So specifically, we could draw like an arrow, and we could draw those 4 energy blocks leaving. Right. Now, when energy either enters the system or leaves it, that specific name for that is called work. Right. Energy entering or leaving. And if it's always going to be caused by a force. And I know there's not a lot of room here, but in this case, since it's rubbing against the ground, that's going to be the force of friction. All right. So what I could also have is, let's say that there's a coffee mug on the ground, and then I decide to pick up that coffee mug. Right? If I were to draw my LOL again, KU, KU, and the ground, it has no kinetic energy, no velocity, no height, so no potential. And then I pick it up, so it definitely has some potential energy. So again, it looks like energy just came out of nowhere, but what ended up happening is just energy went into the system, and the system is the cup. Specifically, what happened is this was work, because energy is going into the system. That's caused by the fact that I applied a force, caused by force push of me to pick up that coffee cup, and that caused energy to go into the system of the cup. All right, so if we look before and after, 4 blocks, 4 blocks, 4 blocks, 4 blocks, energy is still conserved. We're just realizing that it may be in or out of our system before or after. So with that idea in mind, let's look at this example. So a 1 kilogram toy car, I'm automatically going to start to label my values. So its mass is 0.1 kilograms. It's traveling at 1 meters per second. So that looks like it's its initial velocity down a ramp from a height of 0.3 meters. So that looks like it's its height, its initial height above the table. The wheels of the car are taped so that they slide with a friction force for 0.4 newtons. So that's our force over a distance of 0.5 meters. So this is going to be distance. We used to do delta x for this, but for energy, we represent distance as just d. All right, so the question is asking, how fast will the car be going when it reaches the bottom of the track? So by the way, the bottom of the track, that means that my final height, that's my final height, specifically at 0 meters, and it's looking for, in this problem, my final velocity, question mark. So that's what I'm looking for at the end of the day. All right, so I eventually want to solve this, but in order to do so, I need to make it my equation, and in order to make my equation, I have to make my LOLs first. All right, so if I look at the situation without a force, let's do that first because that's what we've been used to thus far, is initially it's on top of it's in the air, so it's on top of a ramp, or it's about to go down a ramp, but it's above the ground, so it has high potential energy. It says it's moving, so I'm going to give it some kinetic. Right. By the way, I could have given different amounts of blocks here. As long as I show that those energies are present, I'm good. Right? And if the cart's frictionless, no energy is going to go in or out. And so at the bottom of the ramp, there's going to be no potential energy, which means that these 3 blocks had to get transferred into kinetic energy at the bottom of the ramp. All right. But this is just a scenario that we've been dealing with thus far. This is the actual scenario that the problem is asking for, where we do have a force of friction. So in this case, it's going to start off the same. Has some velocity at the at the initial height, and since it has an initial height, it has potential energy. But there is friction, right? And if there's friction, that's going to be a force that's going to cause energy to leave my system. So I'm going to label this work caused by the force of friction. All right, so I had 4 blocks of energy in my system originally. 1 leaves, which means that I have to have 3 total here. But since I'm on the ground, no potential energy, which means those 3 blocks have to be in kinetic energy. So since there was some friction, I'm not going to have as much kinetic energy. I'm not going to have as much velocity as if I had if that ramp was completely frictionless. All right. So in terms of drawing our LOLs, everything that I just went through here is step 1, step 2, step 3. So this is a really helpful resource to go back to, but I'm not going to go through them because I just kind of talked about them organically right here. But now what we do is we want to take our LOL and we actually want to make an equation from it. All right, so I'm going to look at my initial L. I have kinetic and potential, so I'm going to write K plus UG minus, in this case, and by the way, it's minus because energy is leaving our system. If energy was going in, like over here, it would be plus, but since it's leaving, minus work. And work is just energy that enters or leaves your system. So that's going to be equal to, at the end, the only energy I have, because it's the bottom of the ramp and it's moving, is kinetic energy. So here is my equation that I'm going to end up using. And if we flip to the next page, we could start to expand that equation. Right? Because all the variables it gives me doesn't tell me what kinetic energy or work is. It gives me these variables, right? Height, velocity, mass. Right? But I know, and you could always use your target sheet to help you out with this, that the equation for K is 1/2 mv squared. So instead of writing K, I'm going to write out the equation for it. Right? And the equation for potential energy is mgh. Right? And that's going to be, again, minus work, but I don't know the equation for work yet. So we're going to draw it up here. So the equation for work is force times distance. Right? If we were to put this in words, work is equal to the force, right, multiplied by the distance force is applied for. All right, so what does that mean? Let's say that I kick a soccer ball, all right, and the soccer ball ends up traveling, I don't know, let's say like 50 meters, right? So that's a distance, but that's not the distance I would put in this equation. When I kicked the soccer ball, maybe it was only in contact with my shoe for, I don't know, let's say like 0.25 meters, so not much distance at all. That's the distance over which that force is being applied for. That's where energy is going to enter or leave the system. It kind of makes sense. Like once that ball leaves my foot, I can't add any more energy to it when it's 25 meters away. All right, so my equation for work is force times distance. And then that's going to be equal to, if we go back to the equation that I wrote right here, and again, this is completely based off my LOL, then that's going to be kinetic energy, which is, again, 1/2 mv squared. All right. So now all I have to do is plug and chug. Like this is 80, 85, even 90% of the way home by making this. Right? You're using your physics concepts to make it. But if we were going to solve for it, 1/2, my mass is 0.1 kilograms. Velocities, 1 squared, plus 0.1, my mass, 9.8 is the gravitational field strength on Earth. It'll always be that when we're on Earth. Right? And my height for my problem is 0.3 meters, right? Which I'm kind of going through it quickly right now, but remember, we wrote down all this info, or you could access all the info in the problem right here. I just want to keep on flipping back and forth. Minus my force, which is, and I am going to flip back right here because this is the first time we're ever doing this. My force is 0.4 newtons, and the distance it's applied for is that 0.5 meters. All right. So 0.4 newtons multiplied by 0.5 meters is going to be equal to 1/2 my mass, 0.1, velocity squared. All right. I'm not going to break down all the algebra here, but if you were to solve, right, remember order of exponent or order of operations, do 1 squared first over here. Right, once you get your answer like velocity squared equals something, make sure to square both sides, and you'll get your velocity to be 1.7 meters per second. If you have questions on the algebra, feel free to ask. Remember, you could also always ask those questions on an assessment too. All right, thanks for watching.